Welcome to the lesson 18 of industrial instrumentation. In this lesson, we will basically cover the pressure sensors. As you know, in the process, actually there are three important process parameters. In fact, we call that is a pressure, temperature and flow. We already discussed temperature and flow in details. Now, in these particular lessons, we will discuss pressure sensors. Even though pressure has a different range, we have a low pressure range, we have a high medium pressure range and for a high pressure range, but in this particular lesson we will basically cover this high and medium pressure. For the low pressures or the vacuum pressures, we will have that will be covered in the lesson number 19. Now, the contents of this lesson is U2 manometer, then you have Bourdeau gauge, which is basically used for high pressure measurement. Excuse me. Then we have bellow gauges, and now we will find mostly this U2 manometer, Bourdeau gauge and bellow gauge, these are basically the monitoring instruments and it is not transmitting, though in the U2 manometer people try to make a monitoring instrument. Then we will discuss the diaphragm gauge. It is very important instruments, it has a direct electrical output, so it is widely used for the pressure measurements. We will discuss the diaphragm gauge. Also, we will discuss the semiconductor diaphragm gauge to some extent. Now, at the end of the lesson, the viewer will know the working principles of C-type Bourdeau tube, metals and alloy used for pressure sensors, detailed analysis of the diaphragm gauge. These are basic things we will discuss, right. Now, before going to the let us first discuss the U2 manometer. What is the basic principles of the U2 manometer? For this, let me take the white page. You see, in the pressure measurements, we make the absolute pressure equal to gauge pressure plus atmospheric pressure. Right. Now, typically this U2 manometer, it looks like a English letter U, that is the name that we have coined it, U2 manometer, and I should say it is one of the oldest pressure measuring devices so far the mankind developed. Still it is used for the monitoring instruments in many process industry, or the estimations of the pressures in many, starting from your in the bioreactors or in the laminar hood or in the actual process. This actually is, and it has a wide range also. Now, typical range for this U2 manometer range from starting from the actually 1.013 bar, as you know. Now, 1.03 bar is equal to 1 atmosphere, as you know, right. It starts from that range. Now, what is the basic principle that let us look at? The basic principle is like this. You see that we have a U2 now this relates to the atmospheric pressure. And this is the unknown pressure which is coming in here. And if the pressure is higher than this atmospheric pressure, obviously what will happen, the liquid, we have a liquid, previously we have a liquid like this, it is the same. Now, once the pressure increases, so what will happen, this liquid column, so now it is both same. So, you see what will happen, that so liquid column will come down here. So, it will come down here and its liquid column will go up, it will go like this, right. These are simple principles, and these particular configurations will measure the gauge pressure. These particular configurations will gauge pressure. Now, suppose the difference of height in the two arms of the U tube is h. So, the pressure P1, the gauge pressure P, I should say will be equal to h d g, where h is the height of the difference of the columns and of the U tube, d is that is in the kg per meter cube, h is in meter, d is in density of the liquid of the manometer or manometric liquid sometimes we call it, that is in kg per meter cube, and g is the acceleration due to gravity, which is in meter per second square, right. So, if you use all these units, it will come Newton per meter square, the pressure, right. Now, at the same time we can measure the differential pressure also with this manometer. It looks like if I measure the differential pressure, it will look like this. See what will happen, you see that we have a U tube as before. So, this is unknown pressure. This is P1, this is unknown pressure also, pressure P2 I should say, this is P1. So, actually the liquid, if the P1 is higher than P2, so what will happen, liquid there is a height of difference, so it will be like this one, it will come like this, right. So, this height, that means starting from this point is h. So, again this P1 minus P2, the pressure is equal to h dg, as before h is the height of the difference of the columns in the manometer, d is the density of the manometric liquid, and g is the acceleration due to gravity. Now, the typical manometric liquid or cheap manometric liquid I should say is water, is easily available, and clean water is, you can use the distilled water, which is it will be clean. Now, there are two problems of using the water, even though it is cheap and it is used in industry. So, the typical problem is that the water will be evaporated very quickly. So, you have always, there should be toppings, that means you have to, whenever it is evaporations, you have to fill it to the point. And secondly, that there is a problem, since it is transparent, water is also transparent, even it is in the glass tube, if the U tube is made of glass. So, it is difficult of viewing. These two difficulties make the waters, simple, waters, very difficult to use in the process actually. Now, what will happen, you can make it colored. So, if you use a colored water, so if you put add some color, so you can also use this particular, you can use manometric liquid as water. Now, there are two problems, that the actual liquid which is coming or the fluid which is coming, if it can get contact with the water, if it reacts with the water, that creates a problem in that type of situations, because you see that in the P1 which we are measuring, and P2 it will be connected to some liquid or some gas. So, in that case, that gas or liquid should not react with water. So, you have to prevent that portions, otherwise that will create problem. Now, typical other industrial manometric liquids are typically these are aniline, then we have carbon tetrachloride, then we have bromoform, then we have mercury, transformer oil, these are all typical manometric liquids, right, typical manometric liquid. Now, another problem with the water, as you know, that means because the density of water is you can say it's I mean less compared to the mercury and other liquids. So, as you know, the P1 is equal minus P2 equal to Hd. We have seen that thing, right? So, the density of water is less compared to mercury. Mercury is 13.6 times the density of water. So, if I use mercury, obviously my pressure range also will be high compared to the water. So, that is the reason people I mean use different for that, as the case applies with we have to measure the different pressure range, obviously the manometric liquid also we have to modify, right. Now, this is we have used we talked about the simple U2 manometer. Now, there are other U2 manometers also which looks like this. You see, we have well type manometer, or it is called the cistern manometers. So, well type manometer looks like this. Instead of U2, what they do actually, see there is a well. We have manometric liquid here. Right, and liquids are here, and if the pressure P1 is P, this is released to the atmospheric pressure. So, the liquid manometric liquid is here, it is going up, suppose this is the height. Now, advantage of this well type manometers or the cistern manometer is that you see I have to measure the height only in this column, not here. The reason is this area is so large, so change of height, because you see in the all U2 manometers, you have seen that U2 manometer, what will happen? If P1 is greater than P2, so liquid in this column will go down and this will go up, is not it? So, both the columns I have to measure this, sometimes it is very difficult, you have to measure this point also this point from some reference level, only that times I will get the height. Now, here what will happen, you see if the pressure P1 is higher than the atmospheric pressure, this liquid will come down by infinitesimal small length. So, what will happen, I have to measure only in this one H. I do not have to bother, I should not bother for that difference of height of the liquid which is in the well, right. So, whenever this pressure will be relieved, the liquid will come down and then again it will come to the, suppose this will be our previous position of the liquids. So, this small difference of height we should not bother. So, that is the advantage of the well type manometer, right, or it is called the cistern manometer. Now, we have another manometers which is called inclined tube manometers or draft gauge. It looks like this. So, we have here, I am sorry, so there should be see here. Now, instead of, so they made inclined tube, right. Now, what will happen, this is the unknown pressure, and this is our atmospheric pressure. So, what will happen, you see the liquid will come down here, now what is the difference between this and the inclined tube manometer and the well type manometer? You see in the well type manometer this column is straight. Now, here what will happen, the liquid, since the height is same, the liquid has to travel a more distance here. So, ultimately what I am getting the advantage of the well type manometer, but the sensitivity here in this case will be higher. So, I can measure a smaller pressure difference, resolutions will also be better, right. So, this is the advantage of this type of manometer. This is called the inclined tube manometer, call it draft gauge. Now, all these manometers, as you know, is basically indicating sort of instruments, as I told you earlier. So, it's won't get any, I mean, electrical output this time. So, this is basically a monitoring instruments, neither transmitting instrument nor recording instrument. Though people tried with the mercury in glass manometer with some electrical output. How? Let us look at. People tried with this, like this one. You see what they did. So, there is a U tube like this one. Liquids are coming in. So, it is a mercury in glass, Ag in glass. Now, what they did, they put a resistance like this one, and these are shorted. Now, what will happen, you know, that when this liquid column grows in height, so one by one this resistance will come in parallel, right, otherwise it is not. So, there will change of resistance whenever there is a change of pressure. Suppose this is P1, P2. So, this change of resistance, this R equivalent resistance, I should say R equivalent will be a function of P1 minus P2. So, that can be utilized to get unbalanced voltage if I put in a bridge circuit. So, that can be utilized to get unbalanced voltage of the as the output. So, that can be calibrated in terms of pressure. But as you know, this is a discrete form. So, in between, suppose in between the two resistance, if there is a liquid column comes in, so it will not get any change until unless this liquid manometer liquid touches this resistance and getting the change in resistance, right. So, these are all about manometer. Let us go back to the other type of gauges. Now, as I told you, we will discuss the Bourdeau tube in more details. The pressure transducers, you see that this, as I told you, this we have even though there is, you won't find the U2 manometer there. So, this is the entire gamut of our pressure transducer. We have a Bourdeau tube, we have two types, we have C type, we have spiral tube, we have a diaphragm. The diaphragms are flat, capsule or corrugated, and we have below, these are differential and absolute. So, these are all the entire gamut of the. Now, let us look at the Bourdeau tube in details, right. You see, this is our common Bourdeau tube transducers, and you can see here. So, we have we will see this one after some time. We have now the cross section of this Bourdeau tube transmitter is like this one, transducer is like this one. Cross section looks like cross section looks like this. Now, if the pressure increases, then what will happen, you know, this will try to make circular. That means it will try to make it circular. Due to this, I mean, it is elliptical initially, now it tries to make circular. This tip of this Bourdeau tube, this is a closed end, this is a free closed end, this is free and this is closed. So, the pressure is coming here, it is going through this and hitting this portion, this oval cross sections or the elliptic cross sections. Then what will happen, this will move up. If it moves down, this tip moves out, then what will happen? So, the sector, okay, we have a sector here, it moves in this direction. If it moves in this direction, there is a gear in which this, you see, this is a gear, you can see this gear, right, this is the gear. So, what will happen, there is a hairspring, because to bring back this this pointer to the same position, what will happen, this needle will go in this direction. How it's, again I am telling, this if I apply the pressure, if the pressure is higher than the atmospheric pressure, this tip will go outside. If it goes outside, then what will happen, this sector will move in these directions. You see, this sector will move in this way. If it moves in this direction, this gear in which this needle is connected, or a pointer is connected, so it will go in these directions, right. So, I will get a change of pressure. It is a very widely used transducers, I should say, for industries. I mean, it is thoroughly, I mean, everywhere, from a cycle store to any process industry, you will find it is a very wide range. It can measure the corrosive liquid pressures of the corrosive liquids also, gas also. So, making this starting from the liquid, gas, air, everything we can measure with this one. And it is over the years people are using, even though this is basically a monitoring instrument, not a transmitting instrument. So, since it is a C, you see this tube is C, we call it C type Bourdeau tube, and this either it is written in PSI, pounds per square inch, or in the kilopascal. Again I am telling you, see the fixed open end, so liquid side, and there is a threaded so that it can put on a actually the vessel in which I am interested to measure the pressure, and it is covered, you cannot see from outside, it is the dial will be on this one, so you cannot see anything from outside, right. Now let us look at to the typical Bourdeau gauge of the, you see this is the dial of the Bourdeau gauge. You can see the dial of the Bourdeau gauge, right. You can see the dial here, fine. This is the dial of the Bourdeau gauge. Now I remove the glass cover, okay. You see here. Now let us look at the back side. See here. Right. So it is the back side. This is a C-type Bourdeau tube. You see this is a C-type Bourdeau tube. Pressure, unknown pressure is coming through this region. This region unknown pressure is coming, and it is coming, and it is, this side is closed in. You see this side is closed, right? And you see with the linkage it is connected to a sector. Sector is here. Now what will happen? You see that when I will move this one, sorry, if I move this one, because this tip will move outside, is not it? So what will happen when the pressure increases? It will move this way. You see the sector will move. There is a hairpin, the sector will move, and if I move, what will happen? You see here, if the sector will, pressure will increase, right? Again it is coming back to the original position. Now you see here, again I am telling, see increasing this position, because now it is in the atmospheric pressure, so that it's, there will no. But if I increase the pressure, you can see here, you see this is a closed end, it is sealed here, because this is a typical Bourdeau, I mean your C-type materials you have. So you see here, this is sealed end, right? And here you see here, now you can see the sectors. Again I will show you. You see here, here. You see the sector is moving. You see the sector. You can see the sector. Okay, its sector is moving. Okay, C tube is coming down, and we are getting. So you have a hair spring also here. You have a hair spring which will bring back the needle, and there is a gear also inside. You cannot see it. I mean from the back side you can see. There is a gear also which is on the actually the needle is fixed on the gear itself, right? So I getting the output. So this is about the C-type Bourdeau tube. Now what will happen? You know that in many situations we have a spiral, that instead of one C I can make it a spiral, several spiral, and at the tip that will be connected to the sector. Now advantage of that type of thing is that you see I am getting the more deflections, because usually this is for the quite high pressure, right? But if I have a longer length of the C tube, because if I make a only single C, I won't get much deflections. So instead of that single C, if I make a spiral, that it does not end here. It comes down these, we have several turns, then it ends. And that closed end now again connected to the lever. You see there is a lever here. You see there is a lever. Okay. There is a sector here. Sector on the back side, as you can see here. Okay. Sectors. Again I am moving it. You see here. Okay. You can see the sector is moving, right? Sector is moving. So this way that measurements are taken, right? So this is all about the, and we have a different shape of Bourdeau tube. We will see the twisted Bourdeau tube. Okay. So this is all about of the Bourdeau tube. Let us go back to the class again, digital class. Now see that this is the Bourdeau tube arranged for absolute pressure measurements. You see what will happen here, we have a case open atmospheric pressures, we have a sensing Bourdeau tube here, okay. This is the applied pressure here. So there are two C tube actually connected back to back. If I connect two C tube back to back, now reference Bourdeau tube sealed at 0 absolute pressure, this is sealed at the 0 absolute pressure, this is sealed, I mean totally evacuated and sealed it, there is no free end, that means there is no questions of giving any input to this, right? Whereas here I am giving the input. So this is, there is a free end, and this is a closed end, right. Now, I mean liquids is going or fluid is going inside. Now, in this particular what will happen, I will get absolute pressure because this pressure will be already deducted. So, it is not a gauge pressure, so it is measuring the absolute pressure. Now, this case is there should be little opening because with reference to the atmospheric pressure, I am this C tube will change its position, right. So, this is another form of absolute measurement for Buddha tube. Let us go back to the next. Okay. This is another one. You see, this is basically an axis of small angular displacements. This is a twisted Buddha tube. Instead of I mean C type Buddha tube, we have a twisted Buddha tube. What will happen if I apply pressure? So, this I mean side will try to move. Again the same principle. This is a elliptic or oval shape. It will try to make it circular. So, this will be rotated. So, in this way also I am getting the small angular displacement that can be amplified mechanically and get the output, right. This is another form of Buddha tube. This is called twisted Buddha tube, right. Now, typically even though as I told you that in the academics we are using SI, industry still people are using this, I mean PSI. Still they call it 1 PSI, 3 PSI. So, you have two things should be side by side. That means both the SI unit as well as FPS unit, right. So, because you know the pounds per square inch is basically FPS unit. So, 1 PSI equal to 6894.76 Newton per meter square, which is equal to 6.894 kilopascal. Bronze pressure springs up to now I talk about the pressure spring. That means what is the material of the C type Buddha tube. We have seen sometimes we are using brass, sometimes using phosphor bronze. Now, depending on the particular range, the different pressure transducer is used. Now, bronze pressure springs up to 4136856 Newton per meter square, beryllium copper spring up to 68947600 Newton per meter square. Then we have a steel and alloy steel spring for pressure range greater than 6894 in 10 to the 4 Newton per meter square. Sometimes you know that the this range of this particular instrument depends not only we should consider the range, but also the environments. Suppose I am measuring the liquids pressures of corrosive liquids. In that type of situations we do not have any use, or we do not have any choice other than using your stainless steel C tube, right. So, these are the different materials of the C type Buddha tubes. Okay. These are the different materials. Okay. These are the different materials of the C type Buddha tubes typically used, and the C type Buddha tube which I have shown in the in just few minutes back is basically the material they are using, the bronze, right, easily available. The beryllium, copper, these are not very expensive, also much expensive than the bronze pressure gauge. Obviously, you can see the range of the bronze is much less than the beryllium coppers, and steel alloy and all these things is necessary depending on what type of environments you are using, what type of pressures in what situations or what conditions you are measuring the pressure. So, that type of situations we will use different types of C tube. But basically these three are the three basic C type materials, and among that bronze is most widely used pressure C tube material. Now, next let us go to the bellow gauges. Bellow gauges is very widely used. You see what will happen here. So, that you see here we have a bellows, here bellows. Now, what will happen, you see this is a closed end, okay, it is closed from all side, is closed from side, this is closed, sorry. Okay, you see here it is closed, right. What happened? Here you see the bellows are, I will show you the bellows. Now, if the pressure increases from this side, if a pressure goes inside, this bellow will squeeze. If it squeezes, then what will happen? This pointer or link will go up, right. So, it will move like this one, you see it will move like this one. If it moves like this one, then what will happen? So, I will get an indication. So, this can be calibrated in terms of the pressure, right. So, this is all about the bellow. So, we can show in the next slide something you see here. The pressure range of the system is determined mainly by the effective area, of the bellows, and the spring gradient. Commonly the bellows are of brass or phosphorus bronze. These are basic material used for the bellows. And bellows, these are basically annular ring and welded at two different ends. I will show you. It is basically annular ring welded at the alternative points. Okay. And bellow gauges are commonly employed for measuring gauge pressures range up to 689,476, that be Newton per meter square, that is 100 psi. Typically, and bellow materials are brass or phosphorus. Brass is most widely used bellow materials, and we can show some elaborate arrangement of these bellows. Let us look at. You see, this is a bellow. This applied pressure is coming down here. So we have a point there. Again, there is a sector, and this needle or pointer is connected on a gear. So this actually there is a teeth of this sector. So you have not shown. We have not shown this thing. Now what will happen? You see, the pressure increases. This bellow will squeeze. This bellow will go up. If this goes up, then what will happen? The sector will move in this direction. If the sector moves in direction, then what will happen? You see that this pointer will move in this direction, right? So this scale can be calibrated in terms of the pressure, right? So this is a pinion and sector gauge movement. This is a connecting link. This is a spring, because they are inside will be something, because once you remove the pressure, this bellow should come to the original position. That is the reason the spring should be inside, and this is a case, and case should be hermetically sealed. That means it should be sealed from on all end. That means from this side there should not be any leak, this side not. As you know, bellows are also used for the pressure switch. That will be discussed later on. Let us go and see one bellows. You see, this is the you see, this is a bellow. See, I am squeezing. You see the pressure. If the pressure increase goes inside through this one, so it will be squeezed. It will be if the pressure increases, then what will happen? You see, if that side, it will be squeezed like this one, right? It will be like this one, right? You see. Now you look at very carefully. These are welded actually joint. This is made of brass. You see, this side is welded. Again, the inner side is also welded, right? This side is welded. The inner side is also welded. So we will get the movement like this one, right? And as you know, the bellows are extensively used for measuring the for using as a pressure switch also. How? You see, what will happen if this is hermetically sealed in the refrigerators? This is typically used for your temperature control, because I can use this particular contact point for the temperature control. Then what will happen? You see, if the pressure increases, suppose this is sealed unit. If the pressure decreases, then what will happen? It will squeeze like this one. If it squeezes, you have electrical output that will be disconnected, right? So you see here how the pressure like this one, it's doing like this, right? If the pressure, outside pressure, if the inside pressure is less than the outside pressure, so it will go like this. Okay, if the inside pressure is less than the outside pressure, it will be always squeezed like this. If the inside pressure, if the pressure giving which is more than the atmospheric pressure, so it will expand like this. You see, I can't expand it, so it will expand like this. Clear? That means in the inside pressures, which have pressure giving, it is more than the atmospheric pressure. I will show you again. It will expand like this, right? So, and this particular bellows is made of brass. This is used for some force balance systems. We have taken that thing to show you. Let us go to the digital class again. Now, the diaphragm pressure transducers, the diaphragm pressure transducer is very widely used, pressure transducers. Actually, we will discuss these particular pressure transducers in detail. Diaphragms are used for low and middle pressure range, so it is 1 to 20 in 10 to the 4 kilopascal, right? Both tension and compression stresses exist simultaneously in the diaphragm gauges, and this allows the use of a 4-active arm bridge in which all effects are additive, which gives both the temperature compensation and large output as well. In computing the overall sensitivity, the expression of tangential and radial stresses cannot be applied to find overall sensitivity this. Since the diaphragm surface is in the state of biaxial stress and both the radial and tangential stress contribute to the radial or tangential strain at any point, the general biaxial strain relations are epsilon r, which is radial strain, equal to SR, which is radial stress, minus nu ST upon E. Similarly, the epsilon T, which is the tangential strain, equal to ST minus nu SR upon E, where ST is the tangential stress and nu SR is the tangential radial stress, and nu is the Poisson's ratio and E is Young's modulus of elasticity. Now, SR can be given by, this SR can be written as 3 PR square nu by 8T square whole bracket 1 upon nu plus 1 minus 3 upon nu plus 1 small r by capital R whole square. ST, that means the tangential stress, 3 PR square nu by 8T square 1 by nu plus 1 minus 1 by nu plus 3 small r by capital R whole square, right, where the P is the pressure difference across the diaphragm. Okay. Now, diaphragm looks like this actually. If I see, that looks like this, they have a stretched diaphragm, right. Suppose this is P1 and pressure on this side is P2, P1 greater than P2. So, this diaphragm will be stretched like this, right. So, the center point deflections, either you can use LVDT or you can use some force strain gauges to sense this particular deflections. So, that is calibrated in terms of pressure, right. Let us look at the lesions. What are the lesions? We have T is the thickness of the diaphragm. This is very important. It relates to the linearity of the sensor. Then we have radius of the diaphragm, or outside radius of the diaphragm. Then we have Poisson's ratio, okay. Position parameter, I am sorry, this is a position parameter, so I will tell you what is that actually. Then we have a SR is the radial stress, ST is the tangential stress, and once the strains are calculated, the change of resistance delta R's of the individual gauge are obtained from the gauge factors, then E naught can be determined from the bridge circuit sensitivity. Now, epsilon T assumes the maximum value at R equal to 0, and the radial strain epsilon R is positive in some regions, but negative in others, and assumes its maximum value at small r equal to capital R. You see here the diaphragm, how it looks. You see, this is the position parameter small r, right. You see here, if I take a, this is the position parameter, right. At any point, what is the deflection, right, and the height at this point, particular point is y, and T is the thickness of the diaphragm, and R is the radius of the total diaphragm, or the inside radius of the pipe. Almost it is equal to the inside radius of the pipe, and at any point from the center point deflection will be the maximum. Okay, these deflections we are calling it YC. These deflections we are calling it YC. So, at any point deflections we are calling it I. From the center at a distance R, the deflections we are calling it Y. When R equal to 0 at the centers, we are calling Y equal to YC, right. Now, see, this is the strain distributions, the diaphragm gauge and its stress distribution looks like this. In both the cases, we have both tensile and compressive stress. Here you see the SR, or the radial stress is given like this one, and radial stress, if you look at very carefully, radial stress is maximum at the circumference, which is compressive. This radial stress is compressive and it is maximum at the circumference, whereas this tangential stress is maximum at the center point. Why I am telling that is very much important. You see, again I am telling you, see that radial stress is maximum at the circumference. So, we will put two sensors at the circumference which will sense the radial strain, and we will put two sensors at the center which will sense the tangential stress, right. and there is some particular strain gauge available for that, which is called strain gauge Rossets. We will come to the details of that. So, this is our diaphragm gauge and stress distributions. Now, flat diaphragm show nonlinearity at large reflections, whereas stretching action adds to the basic bending, causing a stiffening effect. So, this should be the deflection of the central point, which have to be keep minimum, otherwise there will be distortions, right. This nonlinearity in these stresses follows closely the nonlinearity in the center point deflection YC of the diaphragm, for which the following relation is available. This is the relation between the pressure P and YC, because you see all other things are constants. In Young's modulus of the elasticity of the material of the diaphragm is constant, thickness of the diaphragm is also constant, T is constant. Now, nu is Poisson's ratio, that is also constant. R is the radius of the diaphragm, that is also constant. Okay, radius of the diaphragm is a constant. That means if I have a diaphragm here, so this is radius R, right. This is our diaphragm, relation between P and YC. And see, very interestingly, this is our nonlinear term. You have to avoid this thing. That means this part should be very, very small compared to this part. So, you can see very easily, if the YC is very, very small compared to T, if the YC is smaller than compared to, we can neglect this part. So, nonlinearity will be less. If the YC is higher, then the nonlinearity will be higher, that we cannot neglect this term. Whereas, if this term is much less than this term, so we can easily neglect that part, right. So, we will solve some problem how much nonlinearity will be introduced by this, obviously, but always you see the deflections of the deflection of the center point or central point of the diaphragm should be much less compared to the thickness of the diaphragm. So, these two are quite related, YC and T, to eliminate the nonlinearity in the systems. Let us go back again. Okay. By designing for a sufficiently small values of YC by T, the desired nonlinearity may be achieved. However, note that small YC by T, please note, also gives a smaller strains and output voltage, right. Why? It is very clear. You see what will happen if I have a diaphragm like this one. So, I have a deflections like this one, right. So, either I have to change the central point deflection by some LVDT, or there is some strain gauges will be there. So, if the deflection is less, then what will happen? This strain developed also will be less. So, I will get a less outputs, right. So, those things you must keep in mind. Now, deflection at any point, any other point, then the central points, as I told you, at the distance r, y is given by this expression, y equal to 3p 1 minus nu square r square minus r small r square 16 et cube. Okay. What is that? So, let us look at basically. That means, from the central point, suppose I have at any point, I have a diaphragm, now it is deflected like this one. This is our central point. Suppose this I am talking about y. So, this distance is y, this deflections of the central point, and this distance from the center is r. So, that deflections or height is here y at this point, which is at a distance r from the center. For that reason, so our expression of the deflections y can be given by these particular expressions. A special purpose strain gauge Rosset, which has been designed to take advantage of this strain distribution and is widely used in diaphragm type pressure transducers. Two strain gauges will be at the center of the diaphragm, where tangential strain will be maximum, and two strain gauges are installed at the edge of the diaphragm, where the radial strain is maximum. We will show you. You see, this is the typical. Okay. Now, you see here what will happen, you see here, this is at the circumference, you see here, this is R2, it is not coming anyway. So, I can draw it here. I am sorry. What will happen, you see here, this is the, this sensor, these strain gauges and these strain gauges will sense this R2 and R4. It is not coming, this is R2 and this is R4. This will sense the radial strain, right, which is maximum at the circumference. So, that is the reason it is, you see this is a total diaphragm gauge, this is a diaphragm, size of the diaphragm, or I should say this is from this is the distance, this radius R. At two strain gauges are at the center, you see here, this R1 and R3 will sense the tangential stress which is maximum at the central point and which is positive, whereas the radial stress which is at the two extreme positions is basically compressive and it is negative, right, because we have seen in a stress distribution curve, in some case it is positive, in some case it is negative. Strain gauges R2 and R4 are oriented to read the radial strain and placed as close to edge as possible, since radial strain has maximum negative value at this point, as I told you earlier. Since strain gauges R1 and R3 are installed as close to the center as possible, and it will read tangential strain since it is maximum at this point. You see this is our strain gauge, so R1, R3, which is basically sense the tangential stress, R2 and R4 which will sense the radial stress and it is compressive, so it will be negative. So, resistance values are decreasing, here it is increasing, all are active gauges. So, strain gauge Rosset in a Wheatstone bridge, so our output will be quite obviously. In Wheatstone bridge, tangential elements are in arms R1 and R3 and radial elements are in the R2 and R4, right. Okay, radial elements are R2 and R4 and tangential elements are R1 and R3, R1 R3 is a positive, right. So, the output voltage E naught with lambda equal to 2 for the diaphragm sensor using strain gauge Rosset supplied by the manufacturer is as follows. So, you are using advanced, since lambda equal to 2, obviously you can see it is an advanced. So, it will E naught equal to 0.82 PR square 1 minus nu square upon ET square Ex. Or I can say that P equal to 1.22 ET square E naught upon R square 1 minus nu square Ex, where C into E naught, where C is the calibration constant, which is equal to 1.22 ET square R square 1 minus nu square in the excitation voltage of the Wheatstone bridge. Diaphragm strain gauges Rosset installed on backing materials are commercially available in several sizes ranging from 0.45 centimeter to 3.2 centimeter. And the sensitivity of the diaphragm pressure transducers Wheatstone bridge combinations will be given by S equal to E naught by P upon equal to 1 by C equal to 0.82 R square 1 minus nu square Ex ET square. You know that you can measure this reflection by the LVDT also, but we are not discussing. So, we are discussing with the strain gauges. So, this is the sensitivity. The sensitivity you can see that it depends on the power supply or the excitations or the radius, diaphragm, thickness of the diaphragm, Young's modulus, Poisson's ratio is hardly beyond our control, is mostly 0.3 for steel. Unlike other transducers, diaphragm deflection rather than the yield strain determines the limit capital R by T max. It can be mathematically shown that the relationship between the pressure and the voltage will be linear to within 0.3% if the deflection Yc at the center of the diaphragm is less than T by 4. Now, neglecting the nonlinear term, obviously the deflection at the center of the diaphragm Yc can be expressed in terms of the pressure as this relation, right. This already we have given in terms of P. Now, we are neglecting the that cube term, that third, I mean that. So, if we neglect that term, so I will get an expression. So, or I should say it is almost Yc is almost center point deflection is equal to 3 P R to the power 4 1 minus nu square 16 T cube into E, with the restriction that Yc should be less than T by 4, because this is the restrictions we have to follow, otherwise that nonlinearity term we have to introduce here. So, that with this restriction the maximum pressure which I can measure should be less than 4 by 3 T upon R to the power 4 multiplied by E upon 1 minus nu square. You can see this ratio is very important, that means thickness to the radius of the diaphragm is very important to control the maximum pressure, right. Pressure transducer that use a diaphragm sensors are well suited for either static or dynamic pressure measurement, quite obviously. The diaphragm sensor has a very high natural frequency with a small damping ratio because of its low mass and relative stiffness. However, the high frequency limits of the diaphragm pressure sensor depends primarily on the degree of damping provided by the fluid in contact with the diaphragm, because not necessarily we will measure the gas pressures, we can measure the fluid pressures or gas pressures also. In that case also, that damping will be basically controlled by that particular liquid. The resonant frequency of the diaphragm should be 3 or 5 times higher than the highest frequency of the applied dynamic pressure. A diaphragm has an infinite number of natural frequencies, however, the lowest is the only one of our interest we should be in. For clamped edge diaphragm, the vibrating in contact with the fluid having density of rho f, that is the fluid density in which it is in contact. The lowest natural frequency of the or fundamental is given by f equal to 10.21 upon pi r square under the square root et square upon 12 1 minus nu square rho into, and that is in Hertz. This rho is basically the density of the diaphragm material, where E is a modulus of elasticity in Pascal, T is the thickness of the diaphragm in meter, radius of the diaphragm in meter, density of the material of the diaphragm kg per meter cube, rho is the Poisson's ratios. And for steel diaphragm, the equation 1 can be simplified as F equal to 4.912, this I mean in Hertz we are telling, equal into 10 to the power 4 upon into T upon pi r square. Now, another type of diaphragm gauge is available, is called the semiconductor diaphragm gauge, because as you know the semiconductor is very widely used. So, we are using the diaphragm as a semiconductor. Here actually this the entire diaphragm is made of semiconductor material, and what will happen, you know, that where you want to get, because there also the Rosette concept is there, right. So, Rosette concept is there also. What they will do that actually that in that in particular what will happen, you know, that that where you want to make the gauge, in that particular point they dope it, right. So, that way they are making the semiconductor. Now, semiconductor advantage, you know, the sense is because one thing we have noticed that in a diaphragm gauge the less the deflections of the central point or less the deflections of the pressure, so it is better. Now, the problem is if I want to make very low pressure, if the deflections are very small, then I won't get any output, because strain because lambda is equal to 2 and whatever the output unbalanced voltage in the Wheatstone which I will get, that may not be sufficient to measure or calibrate in terms of pressure. Whereas, as you know, in the case of semiconductor strain gauges, the gauge factor is very high. If it is advanced, it is 2, lambda equal to 2. In the case of semiconductor strain gauge, the lambda is 130 or 140. With a such a high value of the gauge factor, advantage is that the advantage we will get that, you know, I can measure a very small pressure, because the deflection at that point may be very small, but I will get a larger unbalanced output of the bridge. So, helping us to measure the low pressure there also, not that low, but the medium pressures, right. So, that is what is inside the diaphragm and semiconductor diaphragm gauge. Let us look at. Because of its small gauge length, and semiconductor strain gauge can be used for constructing very small transducers. These transducers may, for example, be used for measurements of the pressure, and due to their small size would allow measurements of strain at higher frequencies. In diffuse semiconductor gauge, the diffusion process employed in integrated circuit manufacture is utilized. In a pressure transducer, the diaphragm would be silicon instead of metal, and the strain gauges are made by depositing impurities at specific location, as I told you. So, I will not using any metals, I am not using brass, steel, anything. I am using the semiconductor wafer itself as a diaphragm, and where I want the particular strain gauge, that position will be doped, right. As I told that the pressure transducer diaphragm would be silicon instead of metal, and the strain gauges are made by depositing impurities at the specific locations. The use of semiconductor technology in pressure transducer construction has led to the development of a variety of very fast, very small, highly sensitive strain gauge diaphragm transducer. Silicon piezoresistant strain gauges can be diffused, because as you know that in the case of semiconductor strain gauges, the piezoresistive effect is more, right. So, silicon piezoresistance strain gauges can be diffused in a single silicon wafer which forms a diaphragm, right. Now, semiconductor strain gauges have a sensitivity that is 50 times greater, almost 50 times, sometimes even more, because in the case of it is, as I told you, in case of advanced it is 2, but if you use some other, suppose isoelastic which has around 3 to 3.5, so in that case it is 50 times greater than the conventional metallic strain gauges, and because the piezoresistive gauges are integral part to the diaphragm, they are relatively immune to the thermoelastic strain prevalent in the conventional metallic strain gauge diaphragm constructions, right. Now, furthermore, a silicon diaphragm will not creep with age, okay, that is a typical problem with the metal diaphragm, it is not creeping, but not always everything is good in the case of semiconductor strain gauges, thus minimizing the calibration drift over time. However, a gauge failure is catastrophic in the case of, which is in the case of metal strain gauges is hardly it fails, okay, whereas however gauge failure is catastrophic in the case of silicon, and it performance deteriorates with the presence of the moisture. That is I am telling that however the gauge failure is catastrophic and silicon is not well suited to wet environment, right. So, if that is the moist, and it is very difficult to control that what type of environment will be, that might be a wet environment also. So, in the case of I mean if I have a metal gauge, that problem does not arise, but if you use a semiconductor, if it is measuring the pressures of dry air, so in that situation there is no problem, right, but other cases it will be problem, right. And since it is the developments of the, it is not that popular I should say, because after the development of the strain gauge rosettes, 4 strain gauge rosettes which is used for the diaphragm gauge, it is I mean people are more using that sensor than the diaphragm, but diaphragm, that semiconductor diaphragm is that integral part, you do not need any strain gauge rosette there which is to be installed on the metal diaphragm, because you have to wait for some time, because they are drying, because the strain gauge rosette will be available, okay, separately on a backing material, that is to be installed on the metal gauge on the metal diaphragm, and you have to keep using all these adhesives, okay, you have to use that thing epoxy, then you have to dry it, you give the timing for drying, as it happens in the case of other strain gauges, I mean, but that type of situation does not arise in the case of, and since it is factory processed, this entire things you are not using in the laboratory or in the actual process. So, the advantage is accuracy is also will be better. This ends the lesson 18 of industrial instrumentation. In the lesson 19, we will start to make the low pressure measurement.